Alright, welcome back to a new number theory lecture. Are you excited as I am to prove this theorem? Let's prove that there are an infinite number of primes, okay? And we're going to make use of this fact. Let me just ask you this question, have you think about it right now. If you take a bunch of numbers, and then you multiply them together, and you add 1, and you ask the question, hey, is that resulting number divisible by any of these numbers that I multiplied together? Think about that. Is the answer yes or no? The answer is no, right? Because if I check and see, like, is this number divisible by 2? Well, sure, it goes in this many times, but with 1 left over. Same with the others. You see that? There's always 1 left over because we added 1. There's always a remainder of 1. So it's not divisible by any of those numbers. Okay, and we're going to use that in our theorem. So this fun little theorem is proved by contradiction. So we're going to assume that the theorem is false. So assume that there's a finite number of primes, and then we'll end up with a contradiction. The world will blow up, and we will have proved the original theorem. Okay? We'll also make use of the fact that every number, right, it's a multiple of prime factors. Either the number itself is prime, or it's made up of a bunch of tiny primes multiplied together. Okay? So here's our proof. Assume there are a finite number of primes. And from here, we'll derive a contradiction. We're assuming there are a finite number of primes, so that means we can list them out, and the list eventually stops. P1, P2, here are all my primes, P3, all the way to Pn. And what do you know? There's a finite number, so there must be a last prime. Pn is the last prime, right? That's what we're assuming. Weird, but we're assuming it. So based on this and this idea, we're going to get a contradiction. So let's multiply all those primes together. If you tell me there's this many, consider, let's make a number k. K is equal to P1 times P2 times all the numbers up until Pn plus 1. Consider that number k. Okay? So any number, right, any integer is a multiple of prime factors, is it not? Right? So it has to be, the number k must be a bunch of primes multiplied together. A bunch of primes from this list, right? Because those are the only primes. From the list multiplied together. So you're telling me those are the only primes. But, and here's where the fun happens, but none of these primes, none of P1, P2, all the way to Pn, divide the number k. There's always 1 left over, based on our discussion above. Oh man, but none of P1, P2, all the way to Pk divide n. Here. Sorry, Pn divide k. Too many variables. Therefore, we have made a number that either that number itself is prime, that's one option. So, either k is prime, or it's a multiple of primes, but there's one prime in the list that we forgot, right? Maybe multiple. So either k is prime, or there's a prime we forgot to add to the list. There's a smaller prime. At least one. In either case, this list was incomplete. Haha, that's a contradiction. Do you see that? We assumed these were the only primes, and we have concluded that there must have been at least one more. The world blew up. QED. Okay? So there are therefore an infinite number of primes. So that was a fun practice problem for proof by contradiction. Hopefully you found that as fun as I did. It's a very classic proof. Okay? So let me not prove this to you, this next one. Let me give you a hand-wavy proof of it, but it's an interesting theorem, and it's cool to think about. It kind of combines our love for primes and our newfound love for modular arithmetic. Okay? So here's the theorem. If p is a prime number, something weird happens when you have another integer that doesn't isn't divisible by that prime, so a is a number, a is not divisible by p, then if you take a and raise it to p minus 1, believe it or not, you end up with 1. You end up with a number congruent to 1 mod p, weirdly enough. So something about primes is doing something odd to this number. And also that means also that a to the p is congruent to a itself, mod p. And that's something that is not obvious. That's an interesting fact, right? I hope you see that. So here's my hand-wavy proof of why this works. It ends up being the case that multiples of a, when you're taking mod p all the time, they cycle through every non-zero element of zp. And remember what that is. That's the set of all the numbers that you get when you mod by p. So 0, 1, 2, all the way to p minus 1. And I'm telling you that when you take multiples of a number that isn't divisible by p, and you keep doing mod p, oh man, do you end up with, or you keep taking powers of a, sorry, mod p, you end up with all of these numbers in some order, and it keeps on cycling. And it gets to try all of them as well. It cycles through every non-zero number. So let me give you a hand-wavy proof through an example for p equals 5, because we love mod 5. And then let's do a equals 2. So the first number, let's do 2 to the power of 0, right? We're going to end up going to 2 to the power of 4 and show that that is 1. But let me show you how it's cycling. So 2 to the 0 mod 5, that's equal to just 1, right? Because it's 1 mod 5. And then let's keep doing powers of 2. So 2 to the 1 is congruent to 2 mod 5, right? 2 to the 2 squared is congruent to 4 mod 5, because we still haven't gone beyond 5. 2 cubed is where the interesting stuff starts happening. That's 8, but mod 5, this is congruent to 3, right? Because there's 3 left over. 2 to the 4, that's 16. Mod 5 makes it congruent to, oh man, there's 1 left over. So it repeated. You see how the cycle repeated? And it hit all the numbers. 1, 2, 3, and 4. And then it wrapped around. And if you keep on going, like 2, one more time, you end up with 2 once more, okay? And the reason this works is right, because 2 to the 4 is equal to 16. And then we do mod 5, right? And then we take the mod 5. I don't know how I want to show this. I guess it's 2 different things. 16 mod 5. That's equal to 1, right? That is weird. It's cycling through all these numbers. It's an interesting little theorem. Okay? And I guess the hand waviness of my proof is here. So the only way for this cycle to restart is to end up with 1, right? Because then you can go back to 2, and then you can keep on multiplying, okay? The only way to restart and get back to your original number a is to end up with 1, and that lets you complete this cycle again. But it's an interesting observation. I don't think I'm going to prove to you the full little theorem, but feel free to look it up on Wikipedia maybe. It's a fun one. All right, so that's Fermat's little theorem. Let's now talk about some more modular arithmetic things. And this is going to lead us to a very important theorem and a very important algorithm for calculating the greatest common divisor of any 2 numbers. We'll end up with a very efficient algorithm that calculates this. Okay? So here's the theorem. Let's let x and y be 2 positive integers, 2 positive whole numbers. Then, here's the thing that we're going to prove, then the greatest common divisor of those 2 numbers, the biggest thing that divides into both of them, that's actually equal to whatever the greatest common divisor of y mod x and x was. And those are smaller numbers in total. Interesting. So we can kind of like push the problem down the line to some smaller pairs of numbers, and we end up with the same answer. Cool, huh? So that is what we're going to prove, okay? We will prove that every factor, right, divisor is another word for that, every factor of x and y is also a factor of these 2 numbers. Their GCDs are the same, okay? So if that's true, right, if we prove that and it's true, then of course they're going to share their greatest factor, right? Does that make sense? If they share every factor, they also share their greatest factor, okay? So here's the actual theorem that we'll prove. For all f, x, and y, if f divides x and f divides y, then you get this, and then also the reverse, because it's a biconditional. So this is true if and only if this is also true. Okay? F divides x and f divides y if and only if f divides y mod x and f divides x. So you can go in between, right? That is our number. So here's f is a factor, right? F is a factor of x and y if it's a factor of both of these, if and only if they share those factors. So the way to prove this theorem is assume all this stuff, all those arbitrary things, and then to prove a biconditional, remember that a biconditional is just the conjunction of both directions. So first you prove, like, here's A, here's B. You prove A implies B, and also you go backwards, right? And this way, which is equivalent to, right, B implies A, right? So if we prove this direction and this direction, we've proven the entire theorem. Okay, so that's what we're going to prove. And that is useful because this leads to an algorithm, because this is a smaller number, and it'll eventually stop. Hey. So this is actually arguably the first ever algorithm ever created. We'll talk about the history later after we prove it. So let's do the left to right direction. So that's this implies this. So we're going to assume the left side, prove the right side. So that's one direction, and then we'll do the other direction too, right? Next time we'll assume the right side and prove the left side. Okay, so let's do both of those sides. All right, this side first. So we're going to assume this, prove this. Assume. Assume f divides x and f divides y, right? So we need to prove both of these things, that both this is true and this is true. So we get this one for free. Do you see that? So automatically, by assumption, something that we're already assuming. So immediately we get that f divides x. So that's checked off. Well, now all we need to do is prove this one, and we've proven everything. Okay? So let's try and make this happen. Let's try and prove that f divides y mod x. So what does that mean, right? Y mod x. That is equal to, if we go back, way back here, boop, 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 this idea, any number mod another, it's equal to that number plus some multiple of the modulus for some integer multiple. Okay? Let's use that fact. That's going to be important with mods a lot of the time. So that means I can break this down into y plus kx for some k. And this is starting to look like divisible, right? So that's why we're going there. Or some k. So we end up with that. That's nice. Then, okay, that means that y mod x, which we've just determined is equal to y plus kx, that is equal to 1 times y, right? Because there's a 1 hidden out there, plus k times x. And what is this? What is this called in terms of x and y? It's called a linear combination, isn't it? Ooh-hoo-hoo. This is a linear combination. A linear combo, let's say, of x and y. What does that mean? Dun, dun, dun. Let's go back to that theorem. Dun, dun, dun. Not that one. Here we go. So I have two numbers, x divides y and x divides z. Then x divides any linear combination of those two numbers. Hoo-hoo-hoo. What do I have down here? What do I have? I have that I'm assuming that f divides x and f divides y. And I have found that y mod x is just a linear combination of x and y. So therefore, by that previous theorem, f must divide y mod x. Isn't that cool? Therefore, we just use that previous theorem. Because we have these, we know that f divides any linear combination of x and y mod x just so happens to be a linear combination of x and y, we've determined. Therefore, f divides y mod x. Yay. So we're building up a bunch of theorems that we can use later. Wasn't that cool? So that's one direction. Let's prove it the other way so that we can make it so that we can always interchange these ideas. That'll prove this, okay? They share their factors. So, all right, here's another idea. So we have a factor. F divides y mod x, we know now, and f also divides x. Let's prove that f divides x and f divides y. So we just prove both of these separately, okay? So again, assume this. Assume f divides y mod x and f divides x. So again, we need to prove this and this. We're already assuming f divides x, so cool. By assumption again. By assumption. F divides x. So all we need to prove now is f divides y, based on these things that we're assuming. So again, let's break down y mod x, right? Y mod x equals y plus kx for some k, based on our way to break down a mod, or some integer k. All right, let's do our linear combo trick maybe again. Let's make it happen. So let's see here. That is all correct so far. So we've broken down y mod x again. Let us solve for y, okay, in this equation. That'll actually lead us somewhere. So we need to end up with something in terms of y, right? So let's solve for y. All right, so y equals, right, equals y mod x minus kx. And what do you know? This is a linear combination right here. There's a 1. So this whole thing, y, this part, y is equal to something, and that happens to be a linear combination of not x and y this time, but y mod x and x. So this y is a linear combination of y mod x and x. Isn't that nice? Because, based on our theorem, if I know that I assume this, f divides this number and f divides this number, then it also divides any linear combination of those numbers. So f must divide y, because y is a linear combination of x and y mod x, of those two original numbers. Isn't that awesome? We're getting a lot of mileage out of that previous theorem. Therefore, f divides y, and that's our proof. So both of those parts build the whole of the GCD theorem. So for all factors of x and y, if f is a factor of x and f is a factor of y, then it's a factor of y mod x and x. And they share their greatest factor, okay? So that proves this. The GCD, the greatest factor of x and y is the same as the greatest factor of y mod x and x. Isn't that awesome? So with that, we have, if we keep on repeating this process, we end up with what's called the Euclidean algorithm, okay? If we keep replacing GCD of xy with the GCD y mod x and x, eventually this will get small, right? This will get super small. We'll end up trying to calculate the greatest common divisor of 0 and some number z, okay? And, okay, every non-zero number divides 0, right? Because it's always easy to go into 0. Anything does. So that means that whatever their greatest common divisor is, if 0 has every divisor, it's just whatever the greatest one of z is, which is z itself, right? That's the greatest divisor that they share between 0 and z. Okay, I hope that makes sense. So the greatest common divisor of 0 and z is just z, and that's an answer. And because we keep replacing this by this by this, eventually we get GCD of 0 and something. That something is the answer, and these are all equalities, right? Equality, equality. Oh man. This is after some time, right? We just ended up with an answer that is the GCD of the original two numbers. That's an algorithm to find the greatest common divisor. Isn't that so cool? And again, the reason this works is because anything divides 0. Like 1 divides 0, 2 divides 0, right? Everything goes into 0. 3 divides 0, because it's just 0 times anything, right? That's the idea. So, yeah. And then so we take the greatest common divisor of all those. Z is the biggest thing that goes into itself. Okay? So that makes what's called the Euclidean algorithm, or Euclid's algorithm. And it was invented by the dude named Euclid back in the day. And he lived in the BC era. And so this is arguably the first ever algorithm created. It's a very fast one, too. Okay? Let me show you this example now. Okay, so let's calculate the GCD of 80 and 61 using this algorithm. We'll keep replacing x and y with y mod x and x. Okay, so GCD of 80 and 61, that's equal to, so that's my x, that's my y. That's equal to the GCD of 80 mod 61. What is that? Y mod x. Or sorry, 61 mod 80, my bad. Let's do this. Let's cheat again and do this in Python. So 61 mod 80, and because it's smaller, these numbers are just going to swap each other. That's what happens if the first number is bigger. So this becomes 61, and then the other one is the original value over here, so that's 80. And now it'll start doing real work. So that's equal to the GCD of y mod x. So the second number mod the first one. So 80 mod 61, and then 61 again. Okay? So that's 19. Oops. And then we take this one and put it here. 61. Isn't that cool? That's how it's working. So eventually we're going to get down to an answer. And I guess another way I could write it is like we start out here with y equals 61 and x was 80 up here. Then the new y, like we calculated y mod x as well, that ended up being 61 all over again. And now this became the new x, and this became the new y, and that's the kind of process we keep repeating. Okay, and so now y mod x is equal to 19, right? And so that'll be the new x down here. Hopefully that makes sense. So it's always 61, 19, and then we're going to keep doing like 61 and mod 19. Okay, that's how it's going to keep going, moving downwards. So GCD of 61 mod 19, that's 4, and then we put 19 next. So it's always like, eventually they swap, but eventually once they get smaller, you just go down to 4, and then you do 19 mod 4, that's 3, and then you do 4 mod 3, and that ends up being 1. Okay, that's how that's going to work. And then you do like 3 mod 1, what is that? 0. Once you got to 0, the previous thing is your answer, but let me show that to you here as well. So we did GCD of 4 and 19. That is 19 mod 4, which we calculated to be 3. So that's the same as the GCD of 3 and 4 now. And that is the same as the GCD of 4 mod 3, 1 and 3, which is the same as the GCD of 0, right? Because 3 mod 1 is 0, and 1. And so it looks like the final GCD, the final answer, is 1. Okay? So eventually, just get the numbers, write them from small to big, or big to small, and then you can just repeatedly take the mods like this in this chain. And that will eventually give you your answer once you get down to 0. It's the one above 0. Okay? So that is the first idea. That's the extended, or that's the Euclidean algorithm. There's also an extended version of this that we'll get to later. But let me show you this in Racket, because we can totally program this in Racket as well. So here's my Racket code ready to go. Let's do this. Define GCD of two numbers, x and y. That's equal to whatever the GCD of y mod x and x is, right? So we're going to eventually need to calculate that if x is non-zero. So once we hit 0, the answer is whatever is in the second spot. So that can be our base case. So cons equal is x equal to 0, then the answer is y. Then I forgot this case right here. So that's one condition. That's one possibility. Let me match my parentheses now. So if that's true, that's what happens. Then, otherwise, what we do is we give back the GCD of y mod x and x, okay? So modulo yx and x. So the answer is whatever that is. And so it's a recursive function in Racket. Very easy to see that there. And so we can print out display a line after we call GCD of, what were we doing? 80 and 61. Isn't that nice? So that'll be the code. Oops. And then let's run it. Racket GCD.racket. And the answer is 1. Yay! And you can also print out like the intermediate calls to all this stuff. You can be like display line. All right, let's print off. Calling GCD on x and y. And a new line. And we can watch all the recursive calls happen, okay? And it really converges quickly, doesn't it? It first flips them to make the first number smaller, and then it just keeps on doing the mod trick. Right. GCD of 3 and 4 is equal to the GCD of 1 and 3 is equal to the GCD of 0 and 1, and the answer is 1. Yay. Isn't that fun? Same with like 12 and 18. That was like my first example, wasn't it? The GCD of those is 6. Okay, so these numbers, 80 and 61, those are relatively prime, aren't they? Yay. All right, so now my question for you, give this a try. Find the GCD of 42 and 30, and then I'll show you how I might think about it, okay? All right, so it's actually easier to just start writing stuff in a line like this. If you write y first and then x, it actually makes a big difference. Okay, so let's do it that way. Trick. Why am I in a subscript? Let me fix that. Or hint. I don't know. An easy way to do this is write y, then x, and then repeatedly take mods. Okay, that's usually the way you want to do this if you're doing it on paper, because here's x, here's y. Write it backwards, because you're eventually going to do y mod x, right? So y is the 30, x is the 42, and then you're going to do y mod x, so 30 mod 42, and they're just like sitting there, ready to go. Okay, so what's 30 mod 42? 30 smaller, so it's going to be 30 again. And then if the numbers were like this to begin with, now they're going to be in decreasing order, and you're actually going to get actual work done, because then again, these shift, right? This becomes your new x, this becomes your new y, and you see how that's it? Or sorry, this becomes your new x, this becomes your new y, and then you can do y mod x all over again. So you just keep on doing a line of the numbers that are right next to each other. You're doing mods. So now we can do 42 mod 30. Let's just get out of this. Whee! Python. I'll be lazy and use Python. So 42 mod 30, 12. And then we can do 30 mod 12, 6, 12 mod 6, 0. Okay, and eventually we're going to get to 0, and the one before 0, right? We don't usually write the 0. The one before the 0 is the answer. Okay, so that's the fast way of doing it. So write the y first, then the x, and just repeatedly take those mods. Okay, so the GCD 42 and 30, the biggest number that divides into both of them, is 6. And that is the Euclidean algorithm. And here is what somebody thinks Euclid looked like, doing cool geometry stuff. All right, so now let's talk about another Euclidean algorithm. It's beyond the normal one. It's the extended Euclidean algorithm, okay? it turns out that if you remember your work, you save all your work as you were calculating the GCD of two numbers, you can use that work to come up with a linear combination of x and y that expresses the GCD, which is weird. It's not at all obvious how you can make a linear combination of 42 and 30 and get 6, and that's guaranteed. Okay? So that's cool. That kind of comes from the definition of like how we can break down a modulus, how we're using that in these proofs up here. But let me show this to you. Okay, so formally, the idea is if you have two numbers, x and y, two integers, then there are always integers s and t such that the greatest common divisor of those two original numbers is equal to some linear combination times x and y, or of x and y. So s times x plus t times y. We can always find an s and a t to make this work. And I promise this is useful. Let's just know how to calculate it first, and then we'll use it to do cool encryption stuff later. So yeah, what you do is you start with your original work. You do the normal Euclidean algorithm, and then you save all these intermediate steps and you use them to come up with the final answer. Okay? So you kind of work backwards, and I'll show you that in an example. You work backwards in that scratch work. And it all kind of has to do with using the division algorithm to solve for y mod x, because that's what we're always calculating in GCD. Okay, so if we like say that n is y, d is x in this division algorithm, we end up with this kind of thing. So n is y, y equals q is y div x, and d is x plus y mod x. That's what r is. So we just plug all those things in. Then we can solve for y mod x. And that's equal to y minus y div x times x. Okay? And this is a very powerful idea because look at how we're expressing a modulus as a linear combination of the two original numbers. And so we can just keep following that chain as we're building it. Okay? So this will definitely make more sense with an example, so let's do it for 675 and 210. Let's first calculate its GCD as normal, and then we'll do all this scratch work. We'll use this idea to find those coefficients for 675 and 210 that make them become the GCD, whatever it may be. So 675, 210, this is y, this is x, so you write y first. 210, 675, and so then you calculate y mod x. And because 210 is smaller, they're just going to swap places, and now we can do 675 mod 210. 45. And then we can do 210 mod 45, 30, 45 mod 30, 15 left over, and 15 is a multiple of 30. So that's going to give us 0, and so 15 is the final answer. Okay? And so now what we're going to do is we're going to work backwards, go from this way to this way, and come up with coefficients that make these all happen. Okay, so this was our last value of y, this was our last value of x, and this was y mod x. Let's use this idea to create coefficients for this y and this x to make 15. Okay? So this original equation looks something like, if we plug everything in, it looks like 45, because that's our y, right? That's equal to y div, that's equal to, y div x. So how many times does x go into y? Integer division, just once. So that's 1 times x, which is 30, plus y mod x, which is 15. Then we solved for 15, right? So it's really this equation that we're going to use for forever from now on. And so we say that 15 is equal to 45 minus 1 times 30. Okay? That is the coefficient there. So we've just made a linear combination of those two numbers to make 15, and now we can just continue that process left to right, because this was also a y, this was also an x before. Okay? And once we bring all those equations together, we'll end up with coefficients for the original two numbers. Okay? I promise it'll work. So now let's solve for the 30. Let's solve for the 30 in terms of 210 and 45. So 30 equals, it's always 210 minus something. You'll get this pattern with enough examples. 210 minus, how many times does it go into 45? It was 4 times. 4 times 45, which makes sense because 4 times 45 is 180. 210 minus 180, that's my 30. Yay. Okay, see how that's working? So that's 4 times 45. Let me redraw that because that looks a bit ugly. So those are coefficients there. And eventually we're all going to plug these in, okay, for each other. And then we can have it this way. So 45 is what combination of 675 and 210? So it's 675 minus, I think it's 2 times 210. Or no, 3 times 210, according to my notes. Yeah, because that's 630. 675 minus 630 is 45. Cool. So now I have these equations. And do you see how they're all kind of linked? Here is 675 and 210. There's a linear combination of them, but that only equals 45. But that's okay, because here's a 45. I can plug that in and get something involving 210 and 675 still. And then I have 30. I can plug that in here, and then I'll end up with 15 on the other end. Okay? It's going to work out. Let's do more math. Let's copy this. So let's take this, put it on a new slide, and try this algorithm out. So 15, that's equal to 45 minus 1 times 30. And then we can keep on plugging these in, okay? Because I have stuff for 30 and 45. I can plug those in, and then they'll eventually be in terms of 210 and 675, okay? So I got my 30. Let's plug in for the 30 now. So that's equal to 45 minus, what is 30? That's 1 times 210 minus 4 times 45. Isn't that nice? And so now I have 210 and 45, all that stuff. So that's equal to 45 minus 210 plus 4 times 45, which is equal to 5 45s minus 1 210. So there's that. And now I have it in terms of 210. I just need to replace that and make 675. So I have an equation for that. 45 is equal to 675 minus 3 times 210. So I'll plug that in here. 5 times 675 using this equation minus 3 times 210. And then I still have the minus 210. And so now let's get all these by each other. So that's equal to how many 675s? That's 5 of them. 5 times 675. And then how many 210s? I have negative 15 of them and 1 less, so negative 16 of them. Okay. So that's, well, it's supposed to be this. Minus 15 times 210 minus 210. And that's equal to 5 times 675 minus 16 times 210. And what do you know? There's an S value, there's a T value. And those are my original 2 numbers that I was trying to make the GCD out of. And the answer is 15. And we can prove that. These are really working, right? It's 5 times 675 minus 16 times 210. That really does make the GCD of 15. Isn't that awesome? So that's the long process. You just build up these equations, and then you start plugging in, okay? And then eventually you're going to build it up in terms of those original coefficients with enough filling-ins of things, okay? Because they're all going to appear. So with that in mind, with this example and these words, I want you to try it, okay? So try it here. Represent the GCD of 42 and 30 as a linear combination of those 2 numbers, of 42 and of 30, okay? So give that a try, and then I'll do it with you. Okay, so the very first thing you do is always do the normal Euclidean algorithm, calculate the GCD. So this is the y, this is the x, so you draw it. 30, 42, and then it's just going to flip-flop because 30 is smaller. So it becomes 30 mod 42 is still 30. Then we do 42 mod 30, that's 12. And then we do 30 mod 12, that is 6. And then we do 12 mod 6, so that goes in perfectly, that's a 0. So 6 is the right answer. 6 is the GCD of 42 and 30, okay? Then we do our fancy equations. So make this y, make this x, this is y mod x. And express 6 in terms of 30 and 12, and then we'll do the same. We'll shift all these, and express 12 in terms of 42 and 30, building up all of our equations. So 6 is equal to, in terms of 30 and 12, it's 30, right? It's always y minus something times x. 30 minus 2 times x. 2 times 12, because that'll make 24, leaving 6. All right, and then we'll express 12 in terms of 42 and 30 now. We'll do it all over again. 12 is equal to 42 minus, that's just 1 times 30. Okay? And then I can build this up. Okay? I can take this initial equation, start plugging in for all the things that I wanted, 42 and 30. So I don't need to get rid of the 30, but I'll get rid of the 12. Make that in terms of 42 and 30. Okay, so that's the second step. And here's the third. So 6 is equal to 30 minus 2 times 12, which is equal to 30 we keep. We wanted that. That's one of the coefficients, or that's one of the numbers we want a coefficient for. And then minus 2 times, then 12 we can replace in terms of those coefficients we care about. 42 minus just 30, right? And then we can solve for how many of each. So this is 30 minus 2 times 42 plus 2 times 30. Okay? So that's equal to 3 times 30. Not plus, but minus 2 times 42. And there are my coefficients in front of those original numbers to make the GCD. Because this is 90 minus 84. Yeah, that's 6. Cool, huh? It always works. You can always find coefficients for those numbers. Coefficient for 30, coefficient for 42. Isn't that fun? So that is the extended Euclidean algorithm, and now you are pros at it. And I think that's where I want to have us stop today. So there's a lot to take in. Go and practice it all, and then we'll come back next time and get into the meat of encryption. At the very end, we're going to learn about RSA, which is a very popular, very powerful form of encryption, and that'll be a topic for next week. So look forward to that. And now I'm going to go make your lab video, so I'll see you in that.